Hi everyone. I'm Jacksen Narvaez. I'm a bachelor physics student at National University of Colombia, and today my presentation it's about Rusph. This is an implementation of the SPH method in the Rust programming language. First of all, kind of motivation. In the screen, you can see an image of one of the most famous protoplanetary disks. This is HL Tau. In the left, it's an image from observational data from ALMA, and in the right, an image from simulations produced by the Phantom code. So you can see like a lot of similarities, some rings, gaps, and all of this is like to highlight that SPH has become a robust and widely used method in astrophysics. How does this method work? Well, it consists mainly of two approximations. The first one is the kernel approximation. Here we have the integral representation of a function where delta is the Dirac's delta function. So basically we kind of smooth that delta function, replacing it by a kernel function such that to calculate the value of, well, density, pressure, whatever it is, in a point R, we have to take into account a neighbor region to that point. And the second approximation is the particle approximation. It's like a bridge from continuous regimen to discrete regimen. So basically SPH discretizes the system domain in a set of particles. They are not real particles, but mathematical interpolation points. So we calculate the values of any property over those particles. Currently, SPH includes a lot of physics like magnetohydrodynamics, general relativity, radiation, a lot of contributions, but also the simulations are produced with high resolutions. That means that we need high performance codes. And by performance, I not only mean speed, but also safety. And this is one of the reasons why I choose Rust to implement the SPH method. The way I implement the particles are using structures, and I have to say that SPH is a relatively computationally expensive method, so we have to implement parallelisation. For this, I use the Rayon library, and well, this is basically like the workflow of the code. So we read initial conditions from an input file. Then we do the evolutions. For this, we first build the tree. The tree algorithm is it's implemented to find the neighbor particles of each particle. After that, we calculate the characteristic smoothing length of each particle to define like the compact domain. After that, we calculate accelerations. Then we update the particles taking into account boundary conditions. And then we calculate the next time step in such a way that the code is, the system is stable over time. And we storage the results in binary files. So let's take a look of some of our results. For the testing of the code, we implement some standard hydrodynamical tests. The first one is the toy star model, where we replace the normal Newtonian gravitational potential by a linear potential. Here you can see the density profile of the start. In red is the analytical solution, and the black dots are the SPH solution, so they are in very good agreement. We also test the zetoplasm wave. This is like a spherically symmetric explosion of energy. We concentrate energy in the beginning in one single point, and so it suddenly like explodes with spherical symmetry. Here you can see the results. They followed like the same behavior as the analytical solution, and the higher resolution we used, the better results we got. Here are more tests for like shock waves. This is done to test like the efficiency of Rusph to simulate discontinuity. So we have like two fluids with different conditions, let's say density or pressure. And here you also see like the agreement between SPH solutions and the analytical solutions. Maybe there are some discrepancies here because of, well, some dissipation terms and also the resolution we used. Here, we simulate the Kelvin-Helmholtz instabilities. The system is basically consists of two fluids flowing in different directions with different densities. So you can see here the formation of the instabilities. We compare the results with another code, phantom. In the phantom solution, you can see the formation of some vortices that we didn't get in Rusph. One of the reasons is, again, resolutions, but not only that, also initial conditions and dissipation terms. But well, the instabilities are formed, so that was a good result. Well, in the beginning, I said that Rusph is implemented for astrophysical systems. So here we have an accretion disk. This is the simulation of a thin protoplanetary disk. The central star is simulated like a punctual particle with a mass and an accretion radius. In the top, you see the simulation of the accretion disk if we don't include real viscosity. So there is like a numerical instability over the central star. You see the like concentration of particles are around that star, like in spherically in radius symmetry. And we solved that problem, including real viscosity. This is done including the Shakura and Sunjaev viscosity. So you see that the instability just disappears and the system is stable and it evolves over hundreds of orbital periods with no problems. Well, this is about the scaling, the speedup metric. You can see that the results are very close to the theoretical line, and it does not depend on the resolution we used. So, well, this is good, and we implement the simulations up to 40 cores, 40 CPUs. So, well, we got good scaling there. And well, finally, like a comparison between Rust and C++. This simulation was done for the toy star model, and you can see independently of the resolution we use, the number of particles, well, like the performance is almost the same as it was expected, but this is only like a basic comparison between the two codes, between the two languages. So for future works, I still have to implement and go deeper in the comparison between Rusph and other low-level languages like C++. I plan to do like a comparison between memory storage, performance, concurrency of the two languages. And regarding like physical simulations, I still have to include self-gravity. This is crucial for the simulation of protoplanetary disk, especially when the mass of the disk is comparable to the central star mass. And as I said, in most of the results, well, one of the challenge that we are facing right now is the resolution. In the best case, Rusph is able to simulate no more than, let's say, 500,000 of particles. So we plan to improve the performance of the code in such a way that we get like a resolution of more than millions of particles. So, well, thank you so much for your attention. I have to say that, well, I'm not a big expert on Rust, so any comments, suggestions are very welcome.